Hello! So, before we can start really getting into building a ray tracer, and we kind of need to understand a bit of maths, because we're going to have to do a lot of sort of calculations to build this. We need to know what we're doing there. And so most of the maths isn't too complicated. But vectors are something you might not have come across before. So we're going to talk about them because they are absolutely key to building a ray tracer. So the first thing is, what is a vector? So a vector can be thought of as like an arrow. So let's pick an arrow. And this arrow clearly has a direction. But when we think about vectors, we also think about it having a size or a length. They're the same thing, really. And so it's all well and good us having this this arrow, but we need some way to represent it in a computer. And I mean, there are several ways we could approach this. We could think about, well, we'll store its direction in one variable and its size in another. And that makes sense, but it's actually easier to store it a bit differently. So the way we're actually going to represent this is with three numbers, x, y, and z. And you might be asking, how on earth do these relate to the direction, the size, the whatever? They seem completely unconnected. But imagine we have a normal coordinate grid. I'm only going to attempt drawing in 2D with x and y, and we have our vector. So vectors don't actually have a position in space. But if we draw it starting at the origin, at 0, 0, that's a special point. So if we start drawing it there, and we now look at the point where it finishes, so this point here, and we can read off x and y values for that point, and so that is where the x, y, and z that we store comes from. You have to imagine this being not flat in 3D, and then we mark along a third line as well, and so that's where those numbers come from. And we will get back to the idea of direction, size, and all of that a bit later, but for the moment we can think of it as just this list of numbers. And so we don't just want to be able to store vectors and wonder at this list of numbers. We want to be able to actually do stuff with them. So the first thing we want to be able to do is addition. So the way we do this is really nice and really simple. So if we have one vector x1, y1, z1, and we want to add it to another vector, which we'll write x2, y2, z2, we get simply x1 plus x2, y1 plus y2, z1 plus z2. We just add together each coordinate individually. But then what does this actually look like? If we can draw vectors as arrows, then we can draw the two vectors we're adding together as an arrow and the result. And if we do that and we position them in a certain way, we get a really neat drawing. So let's call this vector v and this vector u. Then this is v plus u. So if we draw the vectors as arrows, so let's just imagine some vectors. It doesn't matter too much what we draw. So here is vector v, and let's draw another arrow off here. So that, and this can be vector u. So if we position them so vector u starts at the end of v, then the vector that would start, if we position it to start at v and draw it to end at the end of u, this long one is actually v plus u. So vector addition is a bit like finding the long edge of a triangle from the two short ones, in a way. And we also want to be able to do subtraction. And that looks very similar. But I want to think about this in terms of negative vectors instead. So if we have a negative vector, that is just simply putting the negative sign in front of each part. And visually, if we say this is vector v, then, and this is a picture of vector v, then negative v is the same size but in the opposite direction. And again, the position we put these in doesn't matter, only the direction and the size matters. So where I draw them is purely for convenience. And so the next thing we can do is almost an extension of addition. We can multiply, but we don't multiply two vectors together. We multiply a vector and a number together. So, multiplication, where it is not spelt with two T's. So, if we have a times x, y, z, where a is just going to be a normal, sensible number, like say 2 or 3, it's not a vector or anything like that. We just move a inside each, inside the brackets to each coordinate. And so if, again, if this is the vector v, then, and we draw a picture of v, then AV, well, I really want to pick a number here. Let's say 2. So 2 is going to be the length of v, the length of v again. So 2v is twice the length of v. We've already discussed what happens with negatives. So that negative v is just the opposite direction, but the same length. And so negative 2v would be the same length as 2v and the opposite direction. And then division, well, that's very similar. So in most of the time we won't even write it as division. We'll just write it as 1 divided by a times x, y, z. This isn't because we can't write a vector divided by a number, it's just we often prefer to do it like this to distinguish vectors and numbers a bit more. And so the key thing with this is that whatever you multiply it by, the direction does not change, only the length. The exception being if you have a negative number. But then it's only the opposite direction. It's sort of a special direction then. It's not just any wild direction that you could imagine. And so the next thing we're going to want to do is find this length. So we've talked all about how we change this length. We can change it to anything we want if you pick the right number to multiply by. And we'll do that in just a second. But first we want to find its length. And this is one of the two key things it has that I discussed at the start. So this is clearly quite important. So we write the length with a sort of double bar each side of the vector. This expression here means length. And the way we calculate it is the square root of x squared plus y squared plus z squared. And you might notice that this is familiar to the a squared equals b squared plus c squared, which is the formula for finding the angle of or a length even, of a right angled triangle. And it is in fact exactly the same formula, but in 3 dimensions rather than 2. And it's really neat that you can just add the 3rd dimension on here and it still works. And this A is what we're trying to find. So that's sort of where this equation comes from, and it's neat. And so with length, we can find normal vectors. So a normal vector always has length 1. Its direction can be anything we like, but it has to have length 1. And we usually use normal vectors when we don't really care about the length, when all we're interested in is the direction. And the reason we do this is because the result we get will, when we get onto things like the dot product and cross product later, if we do them with normal vectors, the result is very special. And I will highlight that once we get there. But the way we calculate this, if we have a vector, say let's call it v, we just divide by the length of v, and then you get length 1. So nice and simple. And that will take a vector and turn it into a normal vector with the same direction. So the next thing we have is the dot product. So this, it seems a bit odd at first, but if we have 2 vectors, so not y, so if we have 2 vectors u and v, then the dot product, I'll make that clear, u, v are vectors, then u dot v is equal to the size of u multiplied by the size of v multiplied by the cosine of theta, where theta is the angle between u and v. So, I mean, a good question is, what is this weird formula actually doing? And there are several ways to think about this. The way I like to think about it is it's sort of a measure of similarity. So if you have u and you have v and they're going in a similar direction, you get cos theta being really close to 1, so you get a big dot product. If you have u going off in one direction and v at right angles, okay, this is a really key point. If they're at right angles, then the dot product equals 0. Now this is really key and we'll use it a lot, and it's sort of, they're not similar at all. They're going off in completely different directions, doing their own thing. They're totally sort of unrelated in a way. So the dot product is 0. Now if one is going in one direction and one is going in the other, then you get a negative dot product. This is to sort of say they're kind of similar, but they're opposite. Right? They're not completely different like at right angles, but they're not the same. They're opposite, so we go negative. And another way of thinking about this, which you might prefer, is if we draw u and we draw v, both lined up to start at the same point. And then we sort of draw the line at right angles to u that goes to end in v. Well, this line down here is actually equal to the cosine theta times the size of v. So if you then multiply this length by u, you get u dot v. And what's neat is that it doesn't actually matter which way round we draw this diagram. Whether you draw the right angle triangle with v as the long edge or u as the long edge, you'll get the same result, which is neat. But the most common thing we'll use the dot product for is finding theta. And now this comes on to the normal vectors I mentioned earlier. If we use two normal vectors, then the dot product is cosine theta, which is really convenient. If we don't, then we have to divide by their sizes to get the right angle. And that's one of the reasons we like to use normal vectors. And we will be using the dot product a lot. It's very, very useful for a lot of things. Okay, this is the last thing I'm going to go over now. We're nearly done, and then we can get on to some of the more exciting computer graphics. So the cross product looks sort of similar, but if u and v are vectors, then u cross v is n hat, which we'll get on to in a second, times the size of u, times the size of v, times sine theta. So this bit is very similar to dot product, but we've replaced the cosine with sine, and the effect this has is that now two vectors in the same direction, well, sine theta is small, but two vectors at right angles, sine theta is big. So it's kind of reversed. So this part of the equation is less a measure of similarity, but more a measure of difference. But then there's still this bit here, n hat. So n hat is a vector, which means the cross product gives you a vector, which is different to the dot product, which gives you just a number. And n hat is perpendicular to both u and v. So what that means is that between n hat and u, or n hat and v, you have an angle of 90 degrees. Now it's not possible to do this in 2D space because there's nowhere that really fits, but in 3D space you can kind of go out and you can be at both 90 degrees to both of them and get away from them as quickly as possible. But there's actually two vectors that have this property. No, we also, one last thing, n hat, rather the size of n hat, is equal to 1. So n hat is normal. So we now know the size of u cross v is equal to this bit on the right that's not quite the dot product. But it also has a direction, and to figure out what that is, we need to think carefully about what n hat is. So n hat can be found using the right-hand rule. So if you take your first three fingers, so you have your thumb, you have a finger, and then you have a finger pointing off in another direction. and the other two fingers don't matter. So you line them up. So that's U, that's V. And then your thumb will go off in a very natural sort of direction. You might have to wriggle it around a bit to get it at 90 degrees to both, but then that's the direction of N hat. And that's how you can figure it out if you want to. And so having this dot product and cross product is all well and good. But we need to calculate them. And there's actually a very easy way to do this. It seems like it would be quite complicated to find theta, then put it through trigonometry, and then multiply by all these lengths. It's a lot of work to do. And we still have no idea how to find theta. But we don't actually need to do any of that. There's a really easy, simple way to calculate both of them. So, if I write out the vectors in column form again, then, well, we'll have x1, y1, z1, dot x2, y2, z2. This is going to equal x1 times x2 plus y1 times y2 plus z1 times z2. So we multiply across and then add everything up. And please just believe me when I say that this does equal the dot product. They are always exactly the same thing, and this is how we will find the angle between vectors. We calculate the dot product like this, and then we divide by their sizes, and that's how we find the angle. And the cross product is a bit more complicated. So please bear with me while I write it out. But again, please just believe me when I tell you that it is equal to the cross product. And both of these scary-ish looking formulas, we can just type into the computer and forget about them. So we can just take this formula, we can type it into the computer as a function, and then we never need to worry about what it is again. There we go. This is all the stuff about vectors we need to know. And I apologize if it was a little dry, but this is how we're going to model a huge amount of things within a ray tracer, and this is how we can find out information about them, how we can work with them. So it's really important that we do have this. And so in the next episode, we are going to start talking about rays. So I look forward to seeing you then. Thanks for watching, and goodbye.